organizers for inviting me to tell you about Astrosat and prospect of Astrosat contributing to the field of gravitational wave detections. So I would give you some very early results which would tell you the kind of observation that would be possible in the coming years, which might be of interest to gravitational wave detections. So I would limit myself basically to one of the instruments of Astrosat, which has the largest photon collection area called the Large Area X-ray Proportional Counter. Instead of going into details of science that can be done with this instrument, I would give you, take you through some very early results that we have. In between, I will take a couple of minutes to tell you about, some of our beyond Astrosat programs, and after all of that, I would come to a few areas where LAXPC might be of use as far as gravitational wave detection itself is concerned. Follow up with Astrosat, Barun has already covered. So before Astrosat, going into Astrosat, let me just quickly remind you that there was an experiment almost 20 years ago on another Indian satellite called the IRSP-3, on which 3 X-ray proportional counters were sent, and these detectors worked for about 5 years, and we had observations of many bright X-ray binaries, mostly timing studies. So the current instrument that I will talk about again is similar. There are 3 proportional counter detectors, but much larger in size, much wider in area, and data volume wise and its capacity wise, the current instrument is much bigger, but basically a scaled up version of what we had flown about 20 years ago. So this is the picture of Astrosat. The instrument that I would be talking about is LAXPC, Large Area X-ray Proportional Counter. There are 3 detectors of Astrosat, of LAXPC. These detectors cover an energy band of about 4 to 80 keV or slightly beyond that. If you take the effective area, that's the geometric area multiplied by quantum efficiency, shown with this red curve. And if you compare with the timing instruments of similar kind, okay, that is non-imaging broad energy band large area detectors, the one to compare with is proportional counter array onboard Rossi X-ray timing explorer. And there are a couple of missions before that, Ginga mission of from Japan, which worked between 86 to 89, I think, or 87 to 89. And there was an European mission called Exosat, which was between 83 to 87. Both of those were smaller than RHTPCA. So if you see, this instrument has factor of 3 to 5 larger effective area compared to RHTPCA over much of its energy band. And if you remember, RHTPCA were made of 5 detectors, and for much of its life, it worked with 2 to 3 detectors. So the actual effective area that we got was only about 40 to 60% of what is shown in the blue curve. So that's the basic advantage of having a much larger photon collection area. On Astrosat, among all these 5 instruments, and Varun gave you a lot of details about 2 of these, the cadmium zinc telluride imager and the all sky X-ray monitor. Other than that, there is a soft X-ray telescope with modest effective area and angular resolution. But what sets Astrosat apart from things of this kind which are flown before are the things that I have highlighted in, circled in red. The ultraviolet telescope here has 3 band imaging simultaneously, 1 optical band and 2 ultraviolet band. So anything that you look at, you would get 3 simultaneous images with an angular resolution of 1.8 arcsecond. Okay. That is to be compared with instruments of this kind before, GALEX. GALEX had 5 arcsecond angular resolution. But UVT is probably not the area which would interest gravitational wave astronomers as far as Astrosat goes. This LAXPC instrument, over a wide energy band, it has a very large effective area. So this is the circle that we are mostly interested in today. How does it come? The inside of the instrument is basically this very large wire frame, which is dipped in xenon gas at 2 atmospheric pressure. It's a large 1 meter by 36 centimeter by 15 centimeter volume at 2 atmospheric xenon. That's what collects all these photons, giving us this large effective area. So let me show you some very early measurements of various kinds of neutron stars. Some isolated neutron stars, some neutron stars in low mass X-ray binaries, that is neutron stars with low magnetic field, neutron stars in high mass X-ray binaries which often have very high magnetic field like 10 to the power 12 cores, and some black hole sources. Astrosat was launched, Varun didn't specifically mention the date, 28th of September, and about 3 weeks after that this particular instrument was switched on 19th October. In first orbit it was looking at blank sky when the instrument was switched on, and the following orbit we looked at crab, and within half an hour of this data was downloaded, we had the crab pulse profile, and we knew that as far as timing characteristic goes, this instrument is working fine. The crab pulse profiles were generated immediately. LAXPC 1, 2 and 3, the pulse profiles are exactly as you knew it to be. If you plot the pulse profile in different energy bands, you can see significant energy dependence exactly as was known before. So from beginning, LAXPC timing characteristic at least at millisecond level was quite good as expected. At the same time, so this data was from mere 500 seconds of operation of this instrument, and almost a similar period if you look at the X-ray spectrum plotted here instead of energy channel number. The blue curve shows the X-ray photons when the blue curve shows the spectrum when it was looking at crab, O plotted with the background curve. Okay. So you can very clearly see that Astrosat is working over the entire energy band. You have very large effective area over the entire band. So having that kind of timing capacity, Astrosat, this instrument would allow us to study all sorts of fast timing phenomena and timing phenomena which requires large number of photons. Okay. This is an area that has been very well developed by the Rossi X-ray timing explorer proportional counter array, and Astrosat would be able to pursue all of this, but now in a much wider energy band. For example, things like if you have a very fast rotating neutron star, which would be of interest in for continuous gravitational wave emission, that should be detectable. However, when you have a neutron star which is going around in a binary system, its pulses should be delayed, and that should produce this kind of orbital signature. Neutron stars often go through thermonuclear flashes, during which the X-ray intensity may increase by a factor of 10 or so, shown here by this yellow curve, and then it decays. This rise time typically is few seconds, and the decay time few tens of seconds. As the thermonuclear flash takes place, if it's localized, the fire, the burning area spreads, and this hot spot on the surface of the neutron star can produce what are called burst oscillations, shown here in frequency in red. Around such a neutron star or a black hole, the matter has Keplerian frequency going up to few hundreds to up to a kilohertz or little more than a kilohertz, and any inhomogeneity in the disk structure, for example, can produce kilohertz quasi-periodic oscillations and its bit and so on. This is still an open field, but this kind of signals at kilohertz frequency is something that's very interesting, and so Astrosat would allow us to study all of this going to a much higher energy band that was possible earlier. So those are things from, okay, I showed you results, first results from crab, and now here is a pulse profile from a source which is about 100th time crab, okay, much fainter than crab, and in about 2 kiloseconds of LAXPC observation, you retrieve its pulse profiles, very with pretty high signal to noise ratio. This is data from one of the detectors in 2 successive orbits of Astrosat. So you can see we had very good detection of crab soon after launch, and successively as we go down to fainter and fainter sources, this is result from a source which is about 100th of crab. Okay. Now we have observations of sources which are farther much fainter, and analysis is ongoing, and this itself tells you if a source is about 1/10 of this, we would still be able to detect it confidently, and those are the sources where there might be interest in as far as gravitational wave goes. Coming down to neutron stars with in binary systems where you have accretion, if you have a neutron star with low magnetic field and accreting matter at a modest rate, the infalling material remains as it is, that is, it loses its gravitational potential energy, but it remains a fuel, and occasionally it goes through this thermonuclear X-ray burst. We have looked at several such sources and have detected about 10 or 12 bursts. Here are some from one of these sources, 4U1636 -536. we were fortunate to see we detected 6 bursts and 3 of them form a triplet. Okay. Typically such thermonuclear X-ray bursts, the difference between one to the other is of the order of few hours to half a day, sometimes a day or longer. Here we had detection of one triplet, and there are only few such triplets detected so far. Okay. The time difference between these two is 5.5 minutes. It just happens to be the shortest time difference ever known between two thermonuclear X-ray bursts in any source. We have thermonuclear X-ray burst detection from other sources. Some are very short, like 10 seconds or so. Some are longer, about 30 seconds or so. We have very good measurements of high mass X-ray binaries, where you have a neutron star accreting material from the companion, which has the neutron star here has very strong magnetic field. The infalling material gets channeled onto the poles, and the radiation is anisotropic, so the emission that comes out is pulsed. So if you take the light curve from such a source and produce the pulses over wide energy band going from like 3 keV to up to about 60 keV, you detect the pulses whose profiles are known for these very well studied sources like Vela X-1. However, what comes out very stunningly from Astrosat observations is that if you look at the spectrum of such a source, if we take the phase average spectrum, that is quite featureless. Okay? But the moment we take a spectrum at different phases, what we find is that spectrum from source like Vela X-1 at different spin phase is remarkably different. Okay? It's not only that it's different, it comes out from Astrosat observation with remarkable statistical quality. Okay? So this is raw data. We are now working on the energy response matrix of the instruments, with which we will be able to then measure the spectral parameters. For example, the cyclotron line, which is a measure of the magnetic field strength on the neutron star. And this data is of remarkable quality as far as statistics goes. Okay? If you compare this with anything from other instruments which worked in the hard X-ray band, like NuStar, like Suzaku HXD, this data has much better, basically larger number of photons going into hard X-rays. Another X-ray pulsar which was transient, we had a mere 20 kilosecond observation, and from that we constructed pulse profiles with very good statistical quality. Again, if you look at the X-ray spectrum at different pulse phases, you can see remarkable difference going from one phase to another, which basically means as you are looking into the magnetosphere of the neutron star, as the neutron star is rotating, we are looking at it from different angle, and from different angle the X-ray spectrum is so different. This is probably, as I said, I mean, the statistical quality of this data is remarkable compared to anything that we had seen before. Here is a light curve from this unique high mass X-ray binary Cyg X-3. In spite of being a high mass system, it's very compact with an orbital period of only 4.8 hours, and here is a light curve from Cyg X-3. The energy response of the LAXPC instrument, that's what is needed now to derive astrophysical parameters from those measured spectrum. In the energy range of about 5 to 30 keV, the black curve here shows the total spectrum. Actually, it's lying on a model spectrum for crab. Okay, the match is quite well. However, we quite do not have as good match as we go energy band beyond 30 keV and below 5 keV. That is where the current effort is to improve the energy response matrix, so that we can make use of all of that good quality data to measure astrophysical parameters. The energy resolution of this LAXPC instrument, this is from flight, okay, calibration data. We sign the X-ray detectors with known X-ray photons of 60 keV energy, which gives us a 60 keV peak. And when you have a fluorescence X-ray escaping from the detector, that the same photons can produce a 30 keV peak or a 26 keV peak. The difference between 30 and 26 is noticeable here, which basically tells us the quality of the instrument. It's working with about 10% energy resolution, which was the goal for this instrument. It's working fine. As far as timing characteristic of such an instrument goes, when you have a detector detecting photons at with a constant rate, the time difference between successive events ought to follow an exponential distribution. And for 3 of the LAXPC detectors, this is what we have. Okay, there is no timing anomaly in this instrument. In the initial raw data we had, but all of that correction has been applied, and now we have very clean light curve from this instrument, with which you can, for example, take crab light curve and take a power spectrum. You see the fundamental and very large number of harmonics. We look at the power spectrum of a black hole source. The low power in the low frequency band is from the source. Power in the high frequency band, for these black hole sources, you do not have anything, and therefore the power spectrum is very clean. Okay. Power spectrum being very clean, as you can see here, tells us that when you have features like the kilohertz oscillations and so on, they would really stand out. Okay? You do not have any artifacts in the high frequency band in LAXPC. In low frequency, you do not expect artifacts anyway. This is again power spectrum from a source and different energy bands, and it's for the first time that from very short observations we are able to get power spectrum in hard X-rays. Okay, that was not possible earlier. So Astrosat, for example, the data analysis tools for these are currently in place and would go to public, in open space very soon. I will take a couple of minutes telling you about some experiments that we are doing which are beyond Astrosat. And after that, I will come back to Astrosat again, where we have to describe where we have connection with gravitational wave astronomy. One experiment that we are doing is for measurement of X-ray polarization. Photons bring us information in 4 different ways. One is when you can measure their direction, that's imaging. When you measure their energy, that's spectroscopy. When you measure the arrival time of photons, that is timing. Now, in all of these areas, timing, spectroscopy and imaging, from the early days of X-ray astronomy to today, we have an improvement in sensitivity, okay, by factors of thousands or more. Okay. Like Chandra X-ray Observatory today has a sensitivity for sources with flux of 10⁻15 arcs per second per square centimeter. Compare that with the very early days when it was more like 10⁻9. Okay, there is a million degree, there is a factor of a million improvement in sensitivity. As far as timing goes, we do microsecond timing today with very large instruments. As far as imaging goes, Chandra X-ray Observatory provides you X-ray imaging with 0.3 arcsecond angular resolution, which is almost as good as optical astronomy. Okay. So, timing, imaging and spectroscopy is very well developed in X-ray astronomy. However, polarization is one area, in spite of being very important, it lags behind. Okay. Main reason is that polarization requires detection of a, measurement of polarization requires detection of a very large number of photons. And this is one area where now some very important key scientific questions in X-ray astronomy actually require polarization measurement. Okay. There are a large number of groups working in the world for various kinds of X-ray polarization instruments. The instrument that we are working on is a Thomson scattering X-ray polarimeter that works in the 5 to 50 kV band. There are many instruments, sorry, this is a Windows to Mac conversion problem. There are many instruments working in energy band of below about 8 kV, they use a different technique. There are many instruments working in energy band above about 30 kV, they use a different technique of Compton scattering. In low energy band, you have photoelectron polarimeter where you absorb an X-ray photon in a gas and measure the track of the electron. In Compton scattering and Thomson scattering, the principle is same, but the instruments are different. So the instrument that we have is a Thomson scattering, where you allow an incident photon to get scattered from a low atomic mass scatterer like beryllium or lithium. And after scattering, the photon is more likely to go in the perpendicular direction. And if you rotate this whole instrument around your viewing axis, you will have polarization measurement. So that's the experiment. This is the design, and the prototype has been built for several years. It's very recently, just less than 2 months ago, this instrument, a proposal for a small satellite for this instrument has been approved by ISRO for a launch in about less than 3 years. We are currently working on that. So that is our first beyond Astrosat instrument in the X-ray band. Another instrument that we have started working on also uses our knowledge and expertise that we get while working in astronomy, is the development of a tool with which you will be able to do deep interplanetary navigation with X-ray pulsars. A lot of groups in the world are interested in this. This is a tool that space agencies would be interested in. Imagine, when you are in a flight, you may not really bother about where the aircraft is, because you know that the pilot knows. But if you are told that the pilot doesn't know where the aircraft is, I'm sure that wouldn't be very comfortable. Now imagine deep interplanetary mission, a manned mission. Okay, I think we need to find a better word for that, but with inhabitants in a deep interplanetary mission, and you do not have a clue about where you are. I do not think that will be very encouraging situation. So navigation is something very important. Okay. So today, to do navigation in one direction, it's of course very easy. In the direction of Earth, it's just a ladder, like travel time. but in the perpendicular direction your resolution is quite poor. To get position of the spacecraft in perpendicular direction, you need to do huge coordination between multiple radio telescopes on the ground. It's not real time. You need visibility of the spacecraft. There are a lot of dependencies. Okay. Instead, you can have autonomous, position independent, okay, navigation system with very simple small device, okay, where you have 3 or 4 small X-ray instruments looking at 3 or 4 X-ray pulsars. It's the time difference between pulses from X-ray sources that would tell you the position, and that would tell you the position very, very accurately. So this is something that can be made completely autonomous, and that's where our current effort is. Develop system which is autonomous as far as giving position of a spacecraft is concerned, and we can get to few kilometer kind of position resolution easily with sources like, for example, Crab. Crab pulsar has a very sharp profile. Okay. More sharp the profile is and shorter the pulse period is, better is your position accuracy. So your expected pulsar arrival time is here, your measured time is there, and this time difference basically tells you your position in the direction of the source. And if you look at 3 or more sources, you would know your position. So you do it in multiple directions, and from a large uncertainty area, you can bring down your position uncertainty by factor of 100 to 1000 in each direction, which means you can reduce your volume of uncertainty from factor of 1,000,000 to 1,000,000,000. So that's an instrument under development. The technique currently is under development. We are discussing with ISRO for a future tool like that. Let me go back to Astrosat. So these are kind of post Astrosat activities for us. Astrosat would be good for a whole range of various kinds of studies, and Astrosat is very versatile. You talk to different people working with Astrosat, you would get very different version of what kind of science would come out from it, and which is good. Okay, so Astrosat is versatile, and there are people trying to do very different things with it. My version would be somewhat biased towards things that I am interested in. Today, let me bring those topics related to neutron stars and black holes, and which have some connection with gravitational wave. Astrosat would be good for many rotation powered pulsars. Rotation powered pulsars emit over a very wide energy band, okay, with very significant difference in their X-ray gamma ray spectrum. Okay. Now, a neutron star basically has, let's say, mass. All of the neutron stars probably are identical. You can only have a small difference from neutron star to neutron star. Radius, of course, is probably similar. Okay. So what differs from one neutron star to another is the spin period and the magnetic field strength. Okay. So when you have only 2 variables, how come about a dozen isolated neutron stars provide emission pattern in the X-ray gamma ray band, which is so different. Okay. However, the current observation is taken mostly with integral observatory and RXT observatory isn't quite clear. So this is one band where Astrosat is very good, and it should be able to make such observations for many more sources, or the sources for which it makes observations, the uncertainty will be much lesser. So rotation powered neutron stars would be one set of sources that Astrosat should be good for. Very high magnetic field neutron stars, the Magnetars, with a magnetic field strength of about 10 to the power 15 Gauss, should be another kind of objects where the X-ray emission extends up to like 1 kV to 100 kV, and this is also the energy band where the LAXPC instrument is very, very good. So magnetars are one area where Astrosat should be able to make very quick observations. In particular, many of these magnetars are transient sources. Okay, so when you look at such a source in different intensity states, the changes in their beaming pattern, changes in their X-ray spectrum over this wide energy band, that should give us more clue towards the emission mechanism in such sources. Some rotation powered pulsars, for example, especially the millisecond radio pulsars, many of them, in addition to their very clear main pulse, interpulse, and so on, sometimes they produce what is called giant pulses. Okay, these pulses occur very rarely, but when they occur, they are extremely bright. They could be like 100,000 times brighter than the regular pulse emission, but they occur so rarely that in the average profile they don't really show up. Okay. what has been found in some of these sources, that if you look at the X-ray profiles for these sources, the X-ray pulse actually arrives at the same phase as the radio pulse. Okay. So with Astrosat we have taken up programs where we want to investigate, does the X-ray emission actually come along with the giant pulses? Okay, so far all of these observations were not simultaneous, so you knew that the X-ray emission comes at the same phase as the radio, as the giant pulses, okay, but we do not know whether the X-ray emission itself comes along with the giant pulses, okay. So these are new observations that Astrosat along with GMRT allows us to do and would give us new science. Let me now come to areas which are directly connected to gravitational wave. One kind of sources that I have been interested for a long time are these high mass X-ray binaries. You have this neutron star with high magnetic field that is accreting material and producing pulses. This being in a binary system, you would see the pulse arrival time from the neutron star going back and forth. Okay, this is the signature of the orbit. Once you measure the signature of this orbit again and again and again, and take out the linear component, you often find that there is a quadratic component with a negative curvature, and this is basically a measure of a decay of the orbit of these binary systems. Okay, now such an X-ray binary would naturally decay because there is mass loss from the system, there is very strong wind outflow from the companion star, there is mass transfer from one object to another, but more importantly, in case of high mass X-ray binaries, there is very strong tidal effect. Okay, the neutron star causes huge tide on the companion, and there is angular momentum exchange because of the tidal effect, which brings them together closer. It's just like the Earth-Moon system. Moon causes tide on Earth, but because Earth is rotating faster, it transfers angular momentum to Moon, which is going away. In case of such systems, because the star spins at a slower rate than the orbital period, okay, all of these systems decay, and the decay time scale is 10 to the power 5 to 10 to the power 6 years. Okay. So here is a collage of orbital evolution that has been measured for many different kinds of X-ray binaries. These three are high mass X-ray binaries where we detect orbital period decay. These two are low mass X-ray binaries where we detect orbital period to be increasing. Okay, the two stars are going apart, away from each other. These are the sources which are of particular interest in the context of gravitational wave astronomy, because these are double compact, these are the progenitors of double compact binaries. You already have a neutron star and a massive companion. Okay, eventually the massive companion is going to explode, leaving behind another possibly neutron star in such cases, because the companion star mass is in the range of 10 to 30 solar masses. If the binary survives the explosion, you would have a double compact binary. Okay, so what we have is the rate of evolution, okay, of the progenitors of double compact binaries. Okay, and this rate is significantly higher than the simple evolution time scale of the companion star, and the rate is so high that given the number of high mass X-ray binaries that we see today, okay, one can probably estimate, and you would probably find a very large number of double compact binaries which may have been produced and gone through this phase. So these are progenitors of double compact binaries which would eventually produce by merging gravitational wave and also shock gamma ray burst. So this is one area not very well developed. I mean, you have measurements of evolution of the high mass X-ray binaries, but connecting that to the rate of gravitational wave emitters is one thing that has not been explored in great detail. Astrosat, as I said, it does look at isolated neutron stars, and I understand from isolated neutron stars, very firm upper limits have been put as far as gravitational wave radiation goes from sources like Crab and so on. But of particular interest could be, and Arunabha must have talked about that earlier today, of particular interest could be very young neutron stars. Very young neutron stars with high magnetic field, and many of them are not radio pulsars, so you may not have good monitoring of them in radio. It is Astrosat which may provide a monitoring, that is, during the gravitational wave campaigns, the spin periods of these neutron stars could possibly be provided from Astrosat measurements. So that is one area, some discussions have started, and we might be able to take this up with Astrosat. Among accretion powered neutron stars, if you talk about continuous gravitational wave from accreting neutron stars, the main uncertainty is that if you are to integrate data from either 3 months or 2 years, you need to know everything about the neutron stars, its spin period, its spin evolution, its orbital parameters, and their evolution over that entire period. Okay? And that's a lot of unknown. Most of these sources most of the sources, especially the bright ones, okay, where you expect gravitational wave also to be stronger. So the sources where you have strongest interest are the ones. So this is the mass accretion rate. The flux is X-ray flux is proxy for the mass accretion rate, let us say. The brighter sources, okay, because they are not necessarily pulsating, okay, you do not measure the X-ray pulses from the neutron star, you do not know the period accurately, and therefore you also do not know the orbital parameters accurately, okay. So the number of unknown parameters is so large that if you are to analyze data from a couple of years or even few months, you have to search over a very, very large parameter space. On the other hand, sources which are pulsating also have lower mass accretion rate, okay. So sources where the orbital parameters are known, they are not expected to be gravitationally, strong gravitational wave sources. This is one area where Astrosat may possibly contribute. One source that is of great interest is SCO X-1, which has the largest X-ray flux and therefore mass accretion rate as well. So this is probably the strongest candidate for continuous gravitational wave emission. However, in SCO X-1, practically, other than the binary period, everything is unknown. Okay, you do not know the spin period of the object, and therefore you do not know its evolution. You do not have a good measurement of the orbital parameters. You only know roughly the orbital period. However, there are very, very extensive observations of SCO X-1 with the ROSI X-ray timing explorer. Okay, Astrosat with 5 payloads on it, especially with an ultraviolet telescope, has many constraints. When Astrosat observations are made, it has to meet many constraints, like safety of the ultraviolet telescope, safety of the soft X-ray telescope. These are things that has to be kept in mind. Astrosat doesn't quite get very, very long uninterrupted observations of X-ray binaries, as was possible with the RXT observatory. So therefore, if it's possible, from RXT data, if one gets the spin period of SCO X-1, okay, and therefore gets accurate value of its orbital parameters, then it would be possible to monitor this source with Astrosat much better, okay, and during the next gravitational wave runs. However, coming up with the volume of data that has been generated on Astrosat with on SCO X-1 probably wouldn't be possible anytime in near future with Astrosat, because Astrosat basic science goals are also different. So I would say for gravitational wave, continuous wave sources, one has to probably look into the current archival data in much greater detail and come up with the best cases where further monitoring with Astrosat would be a very good strategy. So SCO X-1 is one source where I know there has already been a lot of effort to dig deep into the RXT archival data, and a coordination between that and Astrosat team probably would be useful. Another source in this context that comes to my mind is not quite as bright as SCO X-1, but this is a source where we have much better control on several of the parameters. Okay? This is a source which is eclipsing. It just happens to be along our line of sight. The orbital plane happens to be a line of sight. So we know its eclipses. We therefore know the orbital epoch very correctly. Okay, it's also an evolving system, but we know its orbital epoch very correctly. We know its orbital period very correctly. Okay, what is not known is the size of the binary. That's one thing. This is a source in which thermonuclear X-ray bursts, during thermonuclear X-ray burst oscillations has been detected with a period of about 550 hertz or so, okay, about 550 hertz. So one knows it's the spin period of the neutron star with an accuracy of, let's say, 0.5% or so. Okay. What one needs to look at is during the non-burst period, search for pulsation of the neutron star after correcting for orbital motion. Okay, that will allow you to handle the entire available data from this object. But when you are trying to correct for orbital motion of the neutron star, the unknown parameters basically are, or the main unknown parameter is the size of the orbit. Okay, so if one allows for a range for the size of the orbit and then makes a very, very deep search for pulsations from this object, this could be an object which one will be able to then follow up with Astrosat, okay, and have very, very accurate monitoring of the spin period and the binary itself, okay, and thereby allow you to make the deepest possible search in an accretion powered neutron star. Okay. All other sources, the parameter space is just too large. Okay. This is a source where one might be able to bring down the parameter space to something that is manageable. Yeah, this is the picture of thermonuclear burst oscillation at around 550 Hertz. So I would leave you with this particular source. It has several parameters known very accurately, the orbital period and the epoch and the inclination of the system. Unknown parameters are spin period is known with an accuracy of, let's say, 1% or better, maybe 0.5%. The size of the orbit is unknown at 30% accuracy. This source has a huge chunk of data from RXT satellite. If one searches for pulsation coherently in the entire data set, okay, by allowing for these two parameters to vary, we might be able to come up with pulsations in this source, and that will allow you to have complete solution for this one X-ray binary and then follow it up with Astrosat. Unfortunately, this source, which was bright from 1985 when it went into a transient high state, it was bright until 2008 or 2009, and then it has gone into quiescence. Okay, but these X-ray binaries, they can come up at any time. So once it comes up, this would be a very good object to monitor with Astrosat. And from the archival data from RXT, this is a source where you have to search in a very small parameter space to come up with complete solution for a binary. So I would leave you with this. This gives us.
Questions?
So a tangential question. In your navigation mission, why X-ray? Why not radio, for example? Why is X-ray better?
In radio, you have many more sources, many pulsars, many millisecond pulsars. They also have very narrow pulse width and so on. So radio would be ideal, provided you can afford very, very large antenna. So in the radio band, you would require huge antenna, and you also have to monitor between, like, there will be reflection from the spacecraft and antenna orientation, etc. So radio, basically infrastructure required is much larger. Even in gamma ray band, you have much larger number of millisecond pulsars, but again the infrastructure is Fermi several tons. Whereas an X-ray pulsar based navigation system can be made in few tens of kilograms and can be completely. You do not need so many sources; just 3 is enough.
Secondly, you mentioned this. You have the time evolution of the several X-ray binaries, which could point to the rates of the compact binary system. That's something looks very interesting.
About 8 to 10 high mass X-ray binaries orbital evolution is measured, and it turns out that most of these have very high rate of orbital evolution, which means they last for a very short period. And we currently have about 200 high mass X-ray binaries in the galaxy. Okay, so that tells us that a lot of systems actually have gone through a high mass X-ray binary phase, and how many double compact systems are left as a product of such HMXBs is something that is working. So currently for double neutron star systems, probably you have the estimation from one side. Okay, you have double neutron stars seen in radio, and from there you estimate what could be the number of gravitational wave system. One can also look at it from the other side.
I have a quick question. So, what is the mass accretion rate for this exoset in its peak time when it was most luminous?
This source is significantly fainter than SCO X-1.
Yeah, so I guess that that's the disadvantage, that its spin down limit will be very.
Yeah, but SCO X-1, as I said, the number of unknown parameters is just.
I understand that. I guess that's the reason this source is not picked up. Otherwise, it's potentially a very interesting source because it has a spin frequency which is pretty much high.
Its spin frequency is quite high.
But
good band for
yeah,
LIGO.
Spin down, it will be difficult to beat the spin down level. So spin down essentially puts a stronger constant, I guess.
Spin down of the?
So since it's actually spin down equivalent of the mass accretion rate.
Okay.
So accretion induced torque is small if you assume that the torque balance.
But SCO X-1 currently is probably just unmanageable. I mean, you hardly know anything about SCO X-1 other than the orbital period.
Yeah. So
whereas this source is one where your parameter space is much under control.
We know, but the gravitational wave emitted by this will be much fainter, I guess, by torque balance limit. But its X1, it may be high, but we don't have a control. Like, we don't know the parameter. That's the main.
In phase which you mentioned at the beginning. So this is basically you just monitor it at different times. How do you probe that?
Spin phase of some of the accretion powered pulsars. So if you see the pulse profile of this source in different energy bands going from like 3 keV to 50 keV is quite different. So if I pick any narrow pulse phase, the number of photons that I have going from soft X-ray to hard X-ray is going to give me the spectrum. And that spectrum naturally is going to be different in different pulse phases, which is then shown here.
If there are no more questions, let's thank all the speakers and we